Welcome to part 2 of this lecture. Part 2 outlines some heuristics that have been compiled to guide process synthesis. As always, heuristics need a health warning. They are not quantitative, not specific, and probably not universally applicable, and may give conflicting guidance. Nevertheless, in the absence of a recipe or other approach guaranteed to find the best solution, heuristics can be useful because they are built on experience of generations of engineers. This slide aims to remind you that many potential process alternatives make process synthesis a challenging problem. The figure on this slide relates to a very simple case where pure feed is converted into one product and one byproduct. Even in such simple case, four configurations may exist, and on top of that, the choice of technology and operating conditions in each of these units are further degrees of freedom that we need to choose. Remember that engineering time needed to investigate each alternative and its variant is costly, because obviously engineering time means money that you have to pay. So we want to find ways to make an efficient use of these resources. So one way to reduce the number of alternatives in chemical process synthesis is to use heuristics. And here we are reminded that heuristics are not perfect, but in spite their drawbacks, the scale and the challenging nature of process synthesis means that they are worth paying attention to. And this section outlines the heuristics presented in the textbook of Cider Cedar. And this book is now available in electronic format via Novel, via the library. The heuristics are grouped into topics listed here, and we will talk about these heuristics in the next slides. And here, if you look at them, you can see that the way these heuristics are grouped are very well aligned with the layers of the onion diagram that we discussed in chapter 1. While these heuristics are not perfect, they do provide a structured way to work through the key decisions while taking into account a range of considerations that apply widely in practice in the engineering of chemical processes, and we will talk about them in the next slides. The first set of heuristics relate to the reactions, and in the first heuristic, we wish to select our materials and reactions to avoid or at least minimize the presence of hazardous materials, and the logic is that if we don't have it, it can leak. In the second heuristic, we wish to eliminate materials that are toxic or hazardous in nature, and we want to consume the reactants to the maximum extent. And this allows us to avoid waste or to minimize the added value to our expensive raw materials. In the third heuristics, we wish to choose conditions and the catalyst to give the best yield to desired product. And in chapter 2 with Dr. Vani, you saw that we as engineers now are allowed to choose temperature, pressure, phase, and the solvent to enhance the reaction. And also, we as designers have the freedom to choose the configuration of the reactor that can actually help us maximize the yield of the product. Fourthly, the heuristic suggests that we can consider hybrid reaction separation units where we have equilibrium limited reactions. And I hope you know by now that the conditions for the reaction and separation need to be similar for hybrid reaction separation to be a possible solution. Second set of heuristics relate to the distribution of chemicals, and the distribution here concerns how impurities and byproducts leave the process, for example, via purge. So firstly, we ask whether we need to have nearly pure products, in particular in the situation where we have inerts present. And the inerts can prevent our product being pure enough, and we could actually remove these inerts either before the reaction or after the reaction. So this heuristic says that it is beneficial to remove the inerts before the reaction for the purpose of obtaining pure product if removing the inert is easy. or if the inerts have a negative impact on the catalyst. So then we want to remove them before the reaction. On the other hand, if the reaction is significantly exothermic, it means that you are going to generate a lot of heat, then we perhaps would want to remove it after the reaction, because then we can use this inert as a heat carrier in the reaction system. The second heuristic on this slide considered species present in small quantities that are also difficult to separate from the mixture. And these species might have entered in the process with the feed in the form of impurities, or they could have been produced in the irreversible side reactions. So the recommendation is that for such trace quantities of these impurities, we can actually use purge to take them out of the system. And here in the final point, it reminds us actually that we can have either a vapor purge or a liquid purge, depending on what we are purging out of the system. And it also depends on the properties of the species in the mixture. Here we continue to consider where to remove the impurities and byproducts from the process. And this third heuristic in this list focuses on the toxic and hazardous species and as well as the valuable species. So it makes sense to recover our valuable species and rather not waste them, because they are highly value-added species. And it doesn't make sense to purge toxic or hazardous species unless we can first maybe remove their toxicity or hazardousness by some reaction first. And we will talk about these issues when we talk about inherent safer design in chapter 6, where we will look at how we can actually make our process safer by removing the toxic and hazardous species from the system. Now, the fourth heuristic, considering distribution of chemicals, relates to the byproducts from reversible reactions. And the recommendation is that if you have a byproduct in relatively smaller quantities, actually you prefer to recycle them. And by recycling this byproduct to the feed, you can actually derive the reversible reaction, avoiding their production in the reaction. And this option can improve the overall selectivity compared to removing the byproduct by separation or purge. The third set of heuristics considers separation, focusing on the choice of technology and the sequencing of separations. And the first two heuristics here considers the phase of the mixture to be separated. And it is recommended that if you have a liquid mixture, the liquid mixture should be separated by distillation, stripping, or liquid-liquid extraction. And the stripping here is normally when you bubble a gas or vapor through the liquid, and as such you remove the compound from the liquid to the vapor phase. And if you have a mixture of vapors, so instead of separating the vapors, first we would want to actually condense the vapors using preferably cooling water, and then we can do the separation by step 1, that is distillation, stripping, and liquid extraction. And if we have no option of using cooling water to condense the vapors, then we might want to consider refrigeration as well. And then again, we will follow step 1. And the reason we are preferring to use cooling water first is because cooling water is considerably cheaper than the refrigeration system. Now, the third heuristic in this set is that we recognize that some gases or vapors cannot be completely condensed, like for example all gases like oxygen, nitrogen, they are very hard to condense. And in these cases, heuristics recommend that we can conduct a partial condensation, that is liquefying the gas or vapor to some extent, and then we can use absorption or membranes to do the further separation. And these three heuristics only looked at the phase of the mixtures, and they not really pay any attention to the species inside the mixture or what are the properties of these species. So I hope, like me, you have doubts about how complete these heuristics are. The fourth category of heuristics considered pressure change, and the first heuristic is that it is much easier and cheaper to raise the pressure of a liquid than that of a gas. And easier here means that there is less enthalpy change involved, and which corresponds to less power required for raising the pressure. And also that the equipment for this pressure change is cheaper and smaller. So actually we are comparing here a pump that is required to raise the pressure of a liquid to a compressor or a blower that is used to raise the pressure of a vapor or a gas. Okay. So obviously pumps are much cheaper compared to compressors and blowers. The second heuristic recommends that if the stream is a vapor, it is beneficial if we first condense it by using ambient medium like cooling water. And once we have the liquid, then we can revert back to heuristic number one, and then we can just pump it by using a pump. The third heuristic considered cases for the gases and vapors that cannot be condensed with ambient cooling like cooling water. And here we consider the pressure change that is needed. So a small change just over 1 atmosphere can be achieved by using a fan. A larger change of around 3 bar can be achieved by using a blower. And the most expensive option is to use a compressor. And even then, the ratio of the outlet to the inlet pressure will be limited. And the range given here is a ratio of 2 to 9. In fact, this ratio depends on the type of the compressor and the properties of the gas. The fifth class of heuristics focuses on the exothermic reactions, and in particular how the heat of reaction can be removed from the system. And the thought bubble here asks, why do we want to remove the heat from the system? Of course, a higher temperature is good for the reaction rates, but at the same time, a higher temperature can also cause some other limitations. For example, high temperature can lead to temperature runaways. It can also lead to equilibrium limitations and can lead to yield limitations if the byproduct formation is stimulated at higher temperatures. It can also exceed the limit of the material of construction, and that can be a big problem, obviously, in terms of the stability of your system. So the first heuristic here considers a highly exothermic heat of reaction, and it is not clear what is defined as high heat of reaction. So this is a bit vague around that. But nevertheless, there are three ways of removing the heat from the reaction or from the reactor are recommended. So the first one is recycling of the excess reactant, recycling of an inert diluent, and using cold shot. And what it means that you can have intermediate feeding points to the reactor so that you can actually lower the temperature of your system. And then we have the second heuristic that considers for more moderately exothermic reactions. And the third bubble again asks, what is the difference, why we need separate rule for highly exothermic and moderately exothermic reactions. And the reason is that in case of moderate exothermic reactions, we expect a gradual increase in terms of the temperature profile, and also we will have relatively low temperatures. And in this case, removing the material and cooling it and then returning it to the system can provide adequate cooling. So we can have like a cooling system for the reactor, so we don't really need to use these methods of cooling because the temperature profile is going to increase much more slowly compared to in this case here. This slide provides heuristics for the opposite case, that is the endothermic reactions, and the heuristics also mirror those of the previous slide. So in the case of reaction that is highly endothermic, we can recycle the material to reduce the temperature change. and the material could be a reactant or an inert diluent. We could also add hot shots, for example, a feed at an intermediate point in the reactor. In other words, we can provide direct heating by mixing of the hot stream with a cooler stream. And then the second heuristic, again, also mirror the one on the previous slide. So in order to boost the temperature of the reactor, we can actually remove the material, heat it, and then return it either between reaction stages or in recycle loop. So just like the case of exothermic reactions, we also divided our heuristics for endothermic into highly endothermic reactions and moderately endothermic reactions, and we have more or less similar solutions here as well. Just some final comments on heuristics. So I hope those heuristics made sense to you and felt useful and usable. The intentions of the heuristics are to give guidance, and the rationale relates to the safety, the control of the reaction, control of flow rates, choice of technologies, and the control of processing costs. The guidance can help to focus our efforts in process synthesis and screen out some options that are unlikely to be advantageous. Although these heuristics are quite useful in terms of reducing the number of process alternatives that we need to evaluate for our chemical process design, but these heuristics have also several limitations. For example, the heuristics can seem quite vague and not clear-cut. There are very few numbers to guide our choices. There is no sense of which decisions trump which others, because in some cases heuristics can be contradictory to each other, and then we are not sure if we need to, for example, follow heuristic A or heuristic B. So we have to then, there is no clear-cut decision on that. In short, heuristics do not give clear, unambiguous, step-by-step approach to arriving at excellent flowsheet design. And in these cases, then as process engineers, we have to use our creativity and rigor and our knowledge from chemical process design to make decisions and put the project in the right direction. And with these final remarks, that's the end of this part on process synthesis heuristics. Thank you for your time.